Hello, my name is Nicolson. I'm here back with the Crank-Nicolson analysis. As you can see on the screen, we have already talked about this in a previous video and how this was another way to basically take the average of those two um, temperature values that was it was a time ahead and a time before, and basically do a calculation on there and take the average of the two values, and then that was going to give you the where you could change the R value, where that R value was the alpha times the incremental change in time divided by the incremental step in position. So with that, as we noticed when we did the algebra, we found that no matter what R that you would have, it would not go off into negative and positive infinity with these oscillations and whatnot. And we will actually see this as well with the code here. And so the way that we want to approach this basically is there was a part with the Crank-Nicolson analysis that you saw where there was a matrix. And if you saw in that matrix, there was three diagonals. There was a middle one, and then there was a top one and a bottom one. And on the top one, if you remember seeing, it was essentially a negative R. And then at the bottom, there was a negative R as well. And then there was going to be the 1 minus 2 R, basically, right there. And then everything else above and below that was just a bunch of zeros. So, and then we had another column to the right of that, basically, was for the matrix multiplication, where it was going to be for the different position values, of course, so you would basically plug in 1, 2, and so on and so forth, and you would generate an equation. So what we're going to do here is we're actually going to do that matrix calculation by utilizing something called SciPy, and you can basically put it in, and it's under the code called solve banded. I actually have it pulled up here, right here. So solve. If you could go to SciPy, you can basically look up and see what that's all about, and then this basically tells you how it'll take those values in the looks like right here the diagonals, and it'll arrange them this way and be able to do the calculations that way and whatnot. You just also, with this code, just have to supply the values, and then from there you just say, okay, well, there's three columns, it's going to be the rightmost term and whatnot, so on and so forth, just through the logic and get through, and you'll be able to actually calculate the matrix via linear algebra. So what we want to do is basically, well, first we want to just say that R is equal to 1. We will get back to this. I can change the R value to whatever we want, but I will actually describe what will happen if we change that R value to a much higher value. So I don't know if I actually, okay, so I already went ahead and did this. I went from scipy.linear algebra import solve banded. I did not have that in the last video, but that's how you basically call on that function right there. And I just kept all the same stuff here, and of course, like we went into, you could always change a lot of these parameters, and it will just, make things even more accurate, or you'll be able to see the graph and see the different iterations with time or a position and whatnot. So what we want to do next here is we want to basically create our array. So how would we do that? So temperature is going to be p dot full, and then we have that nx, the position steps, and then we already said that the temperature is going to be 300 kelvins right there, and we want to keep adding that dot right there because we want it to be floating point, because if we don't have that, then it's going to have some weird things going on. So definitely keep that dot right there. And if you guys remember, actually, from that equation, we were calculating based on a position, or not a position, a time before to calculate the time ahead, and it was r tj plus 1 n plus 1 minus 2 r tj n plus r tj minus 1 n. So it was just going to be the position ahead, the position we're looking at, and the position behind as well. So I'm just mentioning that so we have that. So what do we want to do next? Well, just like the last time, we already know what the temperature is at the very end here, and that was 400 kelvins, and we knew it was 350 kelvins. So we basically want to also indicate that here as well, because we don't want to do any calculations in those areas and change those indexes. We want the value to be what it's supposed to be. So we can just say that that's going to be 350, add that dot at the end, and we can, bit length, it automatically populates when I press, as you'll see again. It'll probably do this again for the next value here. Watch, I'll put 400 and dot in it. It already wants me to do this, so go ahead and press space to avoid that. If you automatically press enter, it auto populates that. Don't catch it, your code can get pretty screwy there. So what we want to do is basically populate that matrix with a bunch of zeros right now. You can do this code called np.zeros. I'm about to type it here, and in the next two areas we're going to see, why don't I just type it out and then discuss it. So you have a, and that's going to be np.zeros, and then it's going to be 3 because we have the 3 diagonals, and then nx minus 2, and the reason why is because we already know what these two are. So we're just basically subtracting those two out, so we don't really need them anymore because we already know them. So we're going to calculate for all the values in between for our matrix, of course. So then what we want to do is also, indicate, so it's going to be from 0 to the end, and that's going to be negative r, because we know that one of the values right there was negative r, and then we knew the other one also in the in another position, in the one position for us is going to be from 1 to the end, and it's just going to be our 1 plus the 2 times the r, of course, because like I just said, we only have 3 diagonals, the rest are zeros there. So then we want to also indicate here, we're just getting out of, get out of my way. So we have a, and then we want to put that it's going to be 1 to the end. And then we want to basically say it's going to be that 1 minus 2 dot times r. So then that's what we have there. Oh man, always wants to do that. So then we have a, and then we want to do the same for the 2. And then we have basically minus r again, because as we remember looking at that Crank-Nicolson analysis matrix, that's how the equation ended up turning out. We only had those 3 diagonals essentially. So, and then this is going to be also negative r. So come on. All right, so there was another column right there, and that was our n, and that's where we're basically calculating. That's the equations that we're developing from this, and that's what the position that we're gonna, or not position, the time before that we're going to calculate, and then we're going to actually create an iteration to get the values ahead, and then we'll be able to actually visualize them on a plot like before, essentially. So we have the b, we can set that equal to np.zeros, and then it's going to be nx minus 2. Same kind of logic, we already know that we already have those 2 values right there. So do that, and then let's go ahead and just say that what our equation is going to be, how it's going to be populated. So it's just going to be put into those indexes from the bottommost to the topmost range. So it's going to be r, we'll just do that, r times t. Basically our equation was the position, it was rtj plus 1, so we have rt, and then so we basically go from 2, and then add to that, we got the 1 minus 2 dot r. Make sure that that's looking accurate. Let me look over the code. I don't have any syntax errors. So then that times this. We can just do the 1 to the negative 1, because it's going to be the j value there, right? And then if it's 2 from the end, 2 from the other one, because we already know the 2 ends. Got to hammer that in, because you don't keep that in mind, then you end up replacing those values. You got some weird stuff going on with your graph as well. So plus r times t, and then we have, man. So then after that, I'm going to go ahead and actually put those values in that 0 vector. Oh, wait. It's b. And then you basically type in the same exact thing right there. And then plus r times t and 0. And then you can essentially just copy this line and do the same thing for the 1, or the position from the end. So that's just going to be -1, -1, and -1. And then next thing, we can just basically look at our plot. Our plot. So we can just call this fig2. You can call it whatever you want, but I'll just call it fig2, you know. Make, as long as you're consistent plots. All right. Let's do enter fig2 and then add scattered x. And I said my x was big. I know sometimes if you don't keep that consistent, then you're going to also have issues. Just make sure everything is always consistent, and then we can just name this, and then just the initial. All right. So then after that, let's go ahead and, all right. Anyways, guys, yeah. I am back, and essentially what I ended up having right here is actually there was supposed to be no equal sign. There was an equal sign on all of these right here, right there, and I also noticed that I had names instead of name written right there. So you got to be very careful with the syntax. As you know, with programming, it's pretty finicky like that. So all right, so we got this right here. Not exactly the most beautiful looking plot that I've ever seen in the world, but hey, at least it's a start right there. So now what we want to do is basically calculate the next amount of values that we're supposed to get through an iterative process right here. So we got this, so now we have the n values. Now we want to generate the next set of n+1 values for the other side of things, and then we're actually going to see the same type of plot that we had before. So what we want to do is, well, what do we do for an iterative? So you say for i in range, and you know, you can pick any number. I'll make it really accurate. I'll say 30,000. How about that? You know, and you can change it to whatever you want, of course. And then basically we want to calculate for that same thing up there. So why don't I just copy this right here, and then if I need to change anything around, I'll take a look at it right there, but it's essentially mostly what we need basically. So we have r times 2t plus, all right, I'm pretty sure it's the same thing, you know, like from what I remember. Yeah, well, we'll see how the graph turns out, but I believe that is the correct equation. I mean, I don't think it would be anything else, so that's the way it's supposed to be. But that's the equation that we're going to be doing for b. And we actually want to get that solve banded part of things to get, you know, to do the calculation over, so for the linear algebra. So before we actually add that equation, I went ahead and just added it so it's there, so we don't have to think about it later. So it doesn't matter when you do things as long as things are going to execute in the proper order. So t, and then we'll say from 1 to -1, solve, banded, and then say from 1, and then 2, and b, and then b. So oh yeah, basically right here, I believe these are going to be essentially the same anyway. So why don't I just save some time and take these, because it's just saying that you're going to keep those values essentially the same because it's their That's how it ends, as I was describing earlier. So that, there, why don't I do this? Then it looks nice. There we go. And then we basically want to just generate it by doing it, saying that if I is, use that mod, basically I was talking about in the previous video, set that equal to 0. Basically, the mod calculation, I went over into that. It's like the remainder thing, and if it's equal to 0, it's going to populate our figure, and then that we're going to be able to actually see the values that are supposed to be on our subplot there. So then we have fig, not to add scatter, and then let's make sure that I don't say names again, but say name, and then we're going to have that it's the F string basically. So F, and then I for the iteration. Yeah, let's close parentheses. All right, and then we have to just fig to show. All right. Let's see our figure doing its calculation here. It's going to put 3,000 right there, of course. That's probably going to take a little bit. All right, and there we go. There is our figure. But see, the interesting thing about this one is going back up, because I was mentioning in the beginning of the video, if I change this R value here, let's say to like 5 and whatnot, and let's just do run all. Maybe I shouldn't have done run all. My computer's not exactly the fastest machine in the world, but it'll be done here shortly. All right, it's down here. All right. And then some stuff starts happening here. And the reason why is because if we looked at that heat diffusion equation where we had, it was the partial of, here, why don't I write it right here? But just imagine the d is like the partial sign. It was like dt over, dt, and that was equal to, the second derivative of time divided by, it was the x, basically del x squared, so del x squared, and that's the proper way to actually write the derivative. But basically the thing is that when you're doing these types of approximations, is that if your delta x, your position, is actually big enough right there, and you change the r value, because when you do a regular derivative, it actually takes the derivative, it's for the infinitesimal amount of change. And basically there's going to be round off error eventually at the end, because you're actually taking finite steps, for the finite differencing, or in this case, it's just +1 here and there, versus taking all the infinite values that are in between. It's basically discontinuous, as with like how calculus works. When you look into calculus, when you have a certain function and you're trying to take the derivative, you're taking the limit as it approaches 0, essentially, until it's like 0.00000, and then as accurate as you possibly want to get it to. But with this method, it is limited because of that. So that's what ends up happening here, and that's basically it right there. And that's how you calculate for Crank Nicolson doing the matrix. And I hope that explains everything, and have a nice day. Bye.